Good morning, everybody. This is lecture 4 in the communication system. Today, I will speak about the AM modulation. I am Amar Abdul Bari. I am with Nearest University. We finished chapter 2 last lecture. Today, I will go in the communication side after we finish the Fourier transform, which representing the giving us the another aspect, another domain to look in the signal that we have, to look in the frequency domain, and we see how many frequencies in our signal, or if we have the frequency side we can get the time domain. So today we will go in the chapter 3, amplitude modulation. So as I said before, modulation meaning that we change some characteristics of the signal or the carrier wave according to the information. So we modulate the carrier wave according to the modulating signal. So we have here, because it's a continuous wave modulation, we have two types here: amplitude modulation and the frequency modulation. In amplitude modulation family, there is a couple, some of them. Amplitude modulation, double sideband suppressed carrier, single sideband, and vestigial sideband. So we will come one by one. So as we learned before, the Fourier analysis is very important and a powerful mathematical tool, and the implementation of analog communication is very simple, and from the side of implementation. However, at the expense of the power and the bandwidth, we will see how that, and we will see that the later analog modulation or amplitude modulation, the later ones is trying to fix these problems, these expenses. Okay, so you should learn by now that there is no free power or free bandwidths. So everything you take a gain on it, you will pay a price for that gain. Okay, in the power, in the bandwidth, in the in the bandwidth itself. If you did not only these traits between the power and the bandwidth, in the bandwidth is limited already. If you have an unlimited power, the bandwidth is limited, so you should care about that. So all the aspects of communication, there is a trade-off between all of them. Okay, so let's see the amplitude modulation. I have here a sinusoidal carrier wave, a cosine 2 by fc t, multiplied by the amplitude AC. Okay, the amplitude is fixed or changed according to the system that you work on. This is C of t. Okay, now the amplitude modulated wave, or after you modulated using the information, then you put the modulation here, AC 1 plus Ka m of t. M of t, it is the signal that we use, the information that we use to modulate our signal, cosine, and K of A is a modulation factor. Okay, so we should keep K of A multiplied by M of t less than 1 for all of t, and F of C should be higher than W. W is the bandwidth of the information, so F of C should be much greater than the highest frequency of the message signal. Okay, then we have in the receiver side, the envelope detector, a device that follow the envelope, follow the signal envelope. So let's see here, if this is the signal, this is the signal that I want to transmit, then if I multiply it and less than 1 plus it, so it will take the shape of the signal itself, of the carrier wave. It will take the amplitude, change on the amplitude only, not changing on anything else. However, it should be less than 1, so it doesn't overlap with the negative side. So see here, this is Ka m of t less than 1, and C it is higher than 1. So here it is very like that it is overlapping, making a this reversal. So the signal coming here, and then there is a reversal in the base, so it start again and return back, there is a reversal again. So there is a change in another characteristic of the signal of the carrier wave. However, we speak about amplitude modulation only, so we only need to change the amplitude, nothing else. Now, if you take the Fourier transform of this signal of S of t, you will see that this cosine. Cosine we speak about cosine before, that it is a delta, two delta, one and at f of c and one at minus f of c. So it is like this, and we have here cosine multiplied by 1 and cosine multiplied by this value, this the signal m of t signal. So m of t already a signal that have an m of f, so we have 4 components here. Okay, m of f, my f of minus fc and plus fc, and here sigma delta and delta. Okay, so here the value the amplitude. So as you remember, cosine 2 by f of c t, it can be expressed in a exponential j2 by fct and a exponential minus j2 by fct, and this exponential you can convert it using the Fourier transform to delta f minus fc. So this is why we change here, and if you multiply by m of t, then this is not delta, this m, this is the signal itself shifted, there is a shift here. Okay, so as you see here that our signal, where is this is our signal, this is the signal that we have in the frequency domain, m of f. And if you multiply it by the carrier frequency cosine, then you will see that it shifted at f of c, and there is a replica in the negative side, it shifted already, and this is the delta, this is the delta at f of c. Okay, so you see also that at f of c there is plus the m signal, it start from fc minus w and end at fc plus w. This is what we call amplitude, bandwidth, sorry. So we have the bandwidth, and also this side we call it upper side band, and this side lower side band. So if you remember that I speak a little about the negative frequency, that the frequency here have a replica in the negative frequency. It is not in the real world, there is no negative frequency, but when we draw it and we work with it, when you see like this, when there is a shift in the frequency domain, then it appear in our in the positive side, and we have to take care, because we take the double the frequency band that we use for the signal. Okay, and this is a problem. So b of t now is equal to 2w. Okay, now signal tone modulation it is, if we have an example here, m of t, I want to send a m cosine 2 by f of m t. F of m t, it's at the frequency at fm. Okay, and this frequency, if you multiply, if you take it in the equation of the modulation, you put it here multiplied by mu. Mu here equal to ka am again. So it meaning modulation factor k, or percentage modulation. Okay, so it is expressed in as a percentage. So to avoid the distortion, it should be less than 1. Again, the same information. So if I divide a max at by a minimum, AC1 plus mu, AC1 minus mu, if you take mu from outside, you can take it by simple calculation. A maximum minus a minimum over a maximum plus a minimum. Now if you take the, for this signal, if you take the here, if you take this one multiplied by this one, and here if you use the basic calculus and cosine, you take it cosine plus and cosine minus, fc plus fm and fc plus minus fm, then take for all this, you have cosine 3. Then if you take it in the Fourier transform, then you will see 6 delta function, and shifted at fc, here shifted at fc plus fm, and here shifted at fc minus fm. Then if you draw this here, and this is our m of t, m signal, this is the fundamental period, or you can see the fundamental frequency, and in the Fourier, the frequency domain, after you take the Fourier transform, you will see 2 delta here, and this is carrier frequency. You see 2 delta at fc at minus fc. Then if you take, this is a modulated signal, then you will see 6 of them here. You will see 6 of them here with different amplitude. Then you will see here what we speak about. This is a very simple example. So if we speak about the power, then you will take the power of this delta, the power. If we speak about the power, then we will take the square of the signal. Then you take the square here, 1 over 2 AC square for the upper side and for the lower side. Then here he draw this against mu to find that the sideband take a huge percentage of the power, and this is the problem of the amplitude modulation, that takes more power and more frequency. Okay, so this is we will skip this. Yes, envelope detection at the receive side. This is the receiver. We speak about, if you remember from the electronics, you take the diode and a symbol. This is a symbol charge and then release, charge and release, charge and release. So this capacitor charge at level, and when it's going up, and it discharge, release the power when it is when the amplitude go down. However, here it's not going down until the other side, so it only follow the envelope. It should be follow the envelope. So this is the output, should follow the envelope of the signal. Okay, so it should be RF plus RSC less than 1 over FC. Okay, and so it should be higher than RLC, the resistor capacitor circuit should be higher than the 1 over FC and less than 1 over W. So it should follow the speed of the signal, it's not charged at very little, so it is not following the speed of the message signal. Okay, so it should be in between, just to follow the signal, the signal of the modulating signal, the message signal. Okay, and not too little, so it's not following the frequency of the carrier itself. So it should be careful with designing this circuit. Okay, now the practical limitation is that the amplitude modulation wasteful power, because you, as you see in the power, is there is a waste of power, a waste of bandwidth. You should only transmit one side band, only necessary for the information, not the two side bands. Okay, so it transmit the bandwidth equal to twice the message bandwidth. So there is three modification. The double side band suppressed carrier, we transmit double side band without the carrier, without the suppress the carrier, without the for reducing the power, but the bandwidth still the same as before. Single side band, we transmit only the upper side band or the lower side band, so you only translate the spectrum of the modulated to a new location without transmitting the power for the for the carrier, and without the lower or the upper. So you transmit only part of the signal. Vestigial sideband modulation, one sideband is passed almost completely and just a trace of the other side. Okay, so this is required slightly instead of the message, so it's not only equal to the total bandwidth of the two sideband, but almost equal to one and something. So we will come later in next lecture to see this tree, but until here you understand what is amplitude modulation and what is the limitation of the amplitude modulation, how it can be calculated and how it can be detected at the receiver, and what is the other type of amplitude modulation that's try to reduce to be more practical. Okay, thank you very much.